Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering. MOSFET switches and logic gates are the fundamental digital electronic devices that create combinational and sequential circuits. N and P MOSFETs, operated in various configurations, create pass transistor switches, transmission gates, latches, and flip-flops. These basic building blocks realize digital functions like data storing, control, and computation operations. In this video, we will discuss N and P MOSFET operation in different modes and configurations, create logic switches and gates, and also study their timing characteristics. Pass transistor logic, PTL, is a configuration wherein transistors are used as on-off switches that either conducts or isolates the in-out digital signals. Popular CMOS logic gate use both N and P MOSFETs and efficiently realize the desired logical functionality. Transistors parasitic like resistance and capacitance, along with the load capacitance, create RC delays. Also, the voltage degradation due to MOSFET threshold voltage further aid in creating delays like rise, fall, and propagation delays. Some of the popular logic gates, along with prominent timing parameters, are shown in the figure. In pass transistor logic, MOSFETs are switched on and off by controlling the gate voltage. The figure shows various regions of operation of a MOSFET. When VGS, the gate source voltage, is 0, irrespective of the input signal, the MOS switch will be in off condition. When VGS is greater than threshold, FET switches on and conducts input to the output. NMOS passes a weak logical 1 signal and a strong logical 0. Hence NMOS is a preferred for transmitting a logical 0 signal. The figure shows various regions of operation of a PMOS pass transistor as a switch. When the gate source voltage VGS is greater than the threshold voltage, for example, close to 0 volts or positive, the PMOS transistor is off and blocks conduction between source and drain. When VGS is more negative than the threshold voltage, the PMOS transistor switches on, conducts between source drain, and transfers the input signal to the output. A PMOS FET passes strong logical 1 to the output, whereas passes a weak logical 0. Hence, a PMOS is a preferred as switch for transfer of logical 1 signal. A MOS switch offers characteristics like high input impedance, voltage control, low control power, compact size, etc. But has demerits like gate source voltage limitation, subthreshold leakage current, gate source capacitance, body diode, threshold voltage variation, etc. Complementary pass transistor logic, CPL, is a design style that improves upon the limitations of traditional pass transistor logic, PTL, by using both NMOS and PMOS transistors in parallel. The complementary behavior of NMOS with strong logic low transfer and PMOS with strong logic high signals transfer improves the signal integrity. Transmission gate with logical low control signal is switched OFF and is driven into high impedance or floating state of operation. With logical high control signal, the FET conducts and transfer the input signal to the output. In complementary mode of operation, both logical low and high signals are efficiently passed on to the output. Complementary pass transistor logic is popular for low power applications and offers advantages over PTL like full voltage swing, bidirectional signal flow, and high speed operation. The MOS transistor structure being symmetrical about its gate, the source and drain terminals are interchangeably used, and the device operation depends on the applied terminal voltages. The parallel N and PMOS transistors of a transmission gates are, respectively, driven by direct and the inverted control signals. Volt swing operation. For low enable signal operation, both the transistors will be in off state, the output is isolated from the input, and the transmission gate operates in a floating state.
For enable high signal operation, both the transistors are in on state.
When the NMOS gate voltage is high, the transistor source to drain distance is low, hence passes logical 0 efficiently, but in passing logic high data suffers from a VTH gate threshold voltage drop. For inverted gate voltage signal condition, PMOS transistor offers low source to drain resistance, efficiently passes logical high level input data to the output. But while passing logic low level data, suffers from gate VTHP, the gate threshold voltage drop. By connecting NMOS and PMOS transistors in parallel, their complementary strengths compensate for each other's weaknesses, transmitting both strong high and low level input data efficiently. Wide output voltage swing property makes the transmission gate most popular in wide ranging of analog and digital applications. The parallel, complementary conducting transistors offer fairly constant resistance. The decreased transistor's resistance will increase the switching speed and reduce the propagation delay. Further advantages of reduced resistance are faster signal propagation, improved signal integrity, reduced power dissipation, bidirectional symmetrical conduction, reduced noise sensitivity, wide voltage range operation, etc. Due to the bidirectional symmetrical conduction property, a transmission gate is used in both analog and digital applications. Input capacitance of a transmission gate is the gate capacitance CGS and the Miller capacitance experienced at the input terminal. Output capacitance is the sum of transistor drain capacitance CGD, Miller capacitance, and the load capacitance. MOSFET's parasitic resistance, capacitance along with the load capacitance combinedly create RC time constant and introduce propagation delay. Typical device parameters data is shown in the table. CMOS inverter is a basic building block of digital devices that employs complementary N and PMOS transistor pair. CMOS inverter converts logical input signal into its inverted output. As shown in the figure, the in-out signal relation is presented through voltage transfer characteristics VTC. Transfer characteristics can be divided into various operating regions, namely less than VIL, greater than VIH, between VIL-VIH transition region and inverter switching threshold voltage level VTH. When input VIN is less than VIL, the output Vout is less than or equal to VO. When input VIN is greater than VIH, the output Vout is greater or equal to VOL. For input lying between VIL and VIH, the output transition lies between VOH and VOL. N and PMOS device size, that is, W by L ratio determines the VTH, the inverter switching threshold voltage. MOS transistor structure is associated with many parasitic, resistive and capacitive elements, which imposes timing constraints on the inverter performance. Some of inverter timing constraints are described below. Time between 90 to 10% of output voltage fall is defined as inverter fall time TF. Time between 10 to 90% of output voltage rise is defined as inverter rise time TR. Time period between 50% of the input voltage rise to output voltage fall is defined as propagation time TPHL. Time period between 50% of the input voltage fall to output voltage rise is defined as propagation time TPLH. Increasing the MOSFET dimensions of W by L ratio increases inverter drive strength and improves switching times. Increasing the MOSFET size increases its input gate capacitance. Inverter input capacitance being sum of N and P MOSFET gate capacitances subsequently increase and thereby increases the inverter propagation delay. Latches and flip-flops are basic bistable devices that are used in sequential circuits for storing and digital data processing. The key difference lies in their triggering mechanism and timing sensitivity. A D-latch is a level-sensitive memory element that stores data enabled by active high or low-level voltage signal. When the enable signal is active, the latch operates in transparent mode and the output Q follows the input D. When the enable signal is inactive, the latch operates in opaque mode and the output Q retains its previous data. A flip-flop is an edge-sensitive memory element that stores data during the clock edge transition of either positive the rising or negative the falling edges only. A data or a delay latch is a fundamental building block in sequential circuits that store and hold data based on the control signal, often referred to as the clock or enable signal. They come in two types based on the level of the clock or enable signal that activates them. A positive level D latch is active when the enable signal is high, that is at logic 1. A negative level D latch is active when the enable is low, that is at logic 0. There are different configurations by which a latch can be implemented and differ in characteristic parameters. A simple configuration of implementing a positive and a negative latch is shown in the figure. A latch consists of a data transmission path and a feedback loop. The data path consisting of transmission gate and the inverter transmits the data. When the path is enabled, latch operates in transparent mode and propagates the data into the latch. Long as the latch is disabled, it operates in hold mode and the feedback loop retains the propagated data stable. A simple schematic of pass edge D flip-flop is shown in the figure. A D flip-flop is made up of two latches connected in a sequence. First, a negative level sensitive latch is connected in series with a positive level sensitive latch. This combination of latches creates a positive edge triggered flip-flop. This configuration ensures that the flip-flop captures input data Dn at the rising clock edge signal only. The first latch, known as master, with low enable signal, operates in transparent mode, propagates the input data D into the latch. The second latch, known as slave, with high enable signal, operates in transparent mode and latches the propagates data to the output terminal Q. The combination of negative and positive level enable signals creates a positive edge transition clock signal. After the clock transition, data transferred into hold mode latches remains stable. Timing characteristics of a flip-flop. To compensate for the inherent delays of transmission and inverters gates and ensure faithful transfer of in-out data, the input data, before and after the clock edge, for a specific period of time, has to be made available and remain stable at the input terminal. The time period before the clock edge is known as setup and after is known as hold time. Some of the setup and hold time periods is known as the timing window of the D flip-flop. Propagation delay of the flip-flop is defined as the time period that elapses between 50% level of input voltage to 50% level of output voltage. Summarizing, semiconductor devices are fabricated on silicon wafers, using insulating materials like silicon dioxide, silicon nitride, and conductive layers like aluminum, copper, tungsten. Depending on the material type used and the physical dimensions, layers exhibit electrical parasitic resistance. The proximity of isolated layers creates parasitic capacitance. Semiconductor devices fabricated with bunch of conductive and isolated layers inherit parasitic elements. Thus, switches and gates fabricated that have built parasitic elements are constrained and impose limitations on the functional and timing performance.
Thanks for your time.
Hope this video has been helpful in appreciating the fundamentals of MOSFET switches and gates performance and their timing characteristics. In the upcoming video, we will discuss further in detail the operation of latches and flip-flops and factors contributing to the setup and hold timing characteristics.
Thanking you once again and hope to meet you in the upcoming video. Bye for now.